next component called bearings for the load transfer from superstructure to substructure. So to recap what we were there, we were looked at the different types of bearing, how the movements are enabled and how they are controlled, both in terms of displacement and rotation. We learned the principles of how we cannot have rotational restriction in all directions simultaneously in the olden type of bearing, and we are now looking at the more modern type of bearings. Now uh, another mechanism which is used to transfer load between. Now what we looked at bearings, they are primarily for vertical load, but they are also capable of transferring lateral loads. They are capable of transferring lateral load. Now we have another set of we can call it articulation, which we use when it comes to transferring lateral loads between superstructure and substructure. So we move forward to that. Let me start by sharing my screen. Please confirm as soon as you're able to see the screen. Okay. So we were looking at the modern type of bearings. The next type of element are STUs. Have you heard of this term STU? Have you heard of it? Yeah. So what is the purpose of shock transmission units? Now we over a period of time we will so we'll have to get the correct terminologies right. Okay. How many of you have used car seat belts? Nobody else. Another example of a shock transmission unit is the shock absorbers. Two-wheelers. You've all driven two-wheelers, and all your two-wheelers have shock absorbers. Correct? So they have slightly different function, but your car seat belt is an ideal example of a shock transmission unit. So how does the car seat belt work? No, it has nothing to do with the brake. The car seat belt. It has nothing to do with the brakes. How do you engage the car seat belt? Let us see if any one of you describes. For the time being, I'll come out of this and let's have a discussion. You can tell me how you engage a car seat belt. Let me ask one question. All of you have traveled on cars? Yes. 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 So that means none of you have used seat belts. And what? Yes, who was speaking? Hello? I have a feeling we'll have to ask everybody to keep in the interaction time, the cameras on. Then only I can make out. Yeah. How do you use the car seat belt? Nobody? At last I'm able to see Shreya's face. How many classes? Third class. The camera problem is solved. So, yes. How many have used car seat belt? It is little shocking to me that you have all sat in car and never used seat belt. I learned my car driving in a place that without driving seat belt, nobody will sit. Huh? Never. So that means you sat in the car but never used. Ah, who was that? I'm not. What about the others? So, okay, I'll explain. You see the car seat belt as sort of, you pull this up. Next time you sit in the car, you experiment with it. You pull it slowly. The belt will get released. You put it into your side lock. Okay. Next, what you do with a sudden jerk, you pull this. With a sudden jerk, you pull it. It will not release. If you pull it slowly, the belt will keep feeding the belt to you. But if you pull it suddenly, it will lock up. Have you noticed this in the car seat belt? So now you understand how the shock transmission units work. When the movement in the girder is slowly, it will allow the movement. Just like your car seat belt, when you pull it slowly, it allows the feeding of the belt. But if you pull it suddenly, in a short time period, then it doesn't feed the belt. In a similar fashion, the shock transmission unit for slow acting movement, it allows the movement. But earthquake type of movement, which has got a very short time period, when you shake the whole bridge for a short time, then the displacements are coming at a very rapid pace. At that time, it locks up and doesn't allow the relative movement between the superstructure and the substructure. So that is how a shock transmission unit works. So you can understand that the principle is used in a very common safety features in car belt. Next time you do the experiment yourself on a car seat belt, okay? Try to engage it slowly and try to engage it. But hurry and you pull it very fast, it will not feed you the belt. You have to slowly pull the belt, then only until it gets locked. And after it is locked, you try pulling the one on your left hand shoulder to try to get it released. It will not release if you pull it fast. OK, so your shock transmission unit is somewhat similar in its function, but this is between the superstructure and the substructure. OK, a typical example of what you see is this. This is a superstructure. This is a substructure. And you have the this is the shock transmission unit. Actually, it looks, that's why I said other equivalents. You can see it is in terms of shock absorbers on your two-wheelers. It's also, you'll see one in the front, which is somewhat similar, but in a different sense, because in the shock absorber, what it does is it controls the displacement. Instead of allowing the displacement to suddenly happen, it allows the displacement to take place in a smaller speed, a smaller velocity of displacement will be reduced, but not like a seat belt. OK, now we will discuss, is this detailing good? Yeah, you can see the screen, but now I would like to hear from you. Do you think that detailing is good? If it is good, why it is good? If it is bad, why is it bad? You have no opinions on anything. Why will not the bolt at the bottom experience the same thing? Just hold on 1 second, please. 1 second. Discussing what is good or bad about that detailing. Shear will always come, whether in the top or in the bottom. But my question was the detailing good as shown there? Now we are full strength. Oh, sorry. Sorry, because I was thrown out of the call by the system. So this is the one. Now you're able to see? So what do you say? What's wrong with the detailing if it is wrong, or if anything is right, what is right about it, please? Most of it is common sense. Please, I think if you're looking for a very high technical question, forget about it. It is a yeah. Go ahead.
It is in one direction only. What
Obviously,
about the other direction?
obviously, they have decided to do this in one direction.
Yes.
We'll come back to that later on when we discuss the articulation, why shock
Mm.
transmission units are used only in one direction. We'll come to that when we look at, we are right now looking at the conceptual stage. But however, I thought since I showed that picture, I want you to have your critical mind active always. So I'm asking you, or rather I asked you whether that detailing is good or bad. I have in fact given you the clue. Okay, at this rate, it will be very difficult. Let me move forward and I'll tell you. See, this is in the longitudinal direction. So what you observed about shear is fine when the movement takes place this side. When the displacement of the superstructure with respect to this in this direction, this will be in tension. When it is in that direction, this will be in compression, right? So if it is tension, then bolt having these gaps is okay. But if it is in compression, do you think this will transmit compression, this type of an arrangement? Yes, no. You don't see any problem here. You don't see this gap. You see, don't see this alignment being done by temporary timber wedges. Absolutely. Your observations should be alert to all these things. OK, so this is a typical example of a shock transmission unit, which essentially works bidirectionally. When the relative displacement, this is the pier, this is the superstructure. If the superstructure moves to the right, this engages in tension. If the superstructure moves to the left, it will engage it in compression. So the detailing must be good for both. And as you're right, somebody has rightly observed, there'll be shear in that. The bolts are designed to take care of the shear. Now, how does this shock transmission unit actually work? OK, it works with it's a two chamber. Basically, you can say that there are two chambers with a piston with a very small orifice. You can see a very small orifice. It has a viscous fluid in that. And when the displacement take place, if the displacement is slow, the viscosity permits in such a fashion the flow of the fluid from this, let us say this as your marked displacement is in this direction. This piston will move this side. If the velocity of displacement is slow, then the fluid will be able to flow in this from left hand side to the right hand side, thereby permitting movement. But if this piston moves at a very fast pace, this orifice is not big enough to allow the fluid to escape from right chamber to the left chamber at the same speed and thereby locking it. OK, this is how a shock transmission unit actually works. And if you want to look at the force versus, what is the force versus displacement graph? That means if I apply a force versus displacement, if this want to look at the graph, If it is a low velocity, the force doesn't increase beyond one small value for whatever the displacement. If the velocity of displacement as velocity associated displacement is low, then this will be the graph. What does this mean? As the displacement increases, the force goes up to a certain point and steadies. If the movement is at a medium velocity, then the force and displacement will linearly increase. And if the movement is a very high velocity, as in the case of a seismic event, then what happens is the force increases exponentially while the displacement increases by a very small amount, which means between the superstructure and structure, locking has taken place. This is the fundamental behavior of a shock transmission unit. So now this is good for what? This is good for only transmitting longitudinal forces between the superstructure and substructure. And when do we use it? We tend to use it when we have long continuous unit in which we have designed one fixed pier. But in the case of an earthquake event, that means if it is in a very high seismic zone, and if you have only one fixed pier, what does it mean? All the inertial forces will go to what? To which foundation? Which foundation? If it's a long continuous structure and it has one fixed pier, all the longitudinal inertial force will go to which foundation?
Fixed pier.
Exactly, to the fixed pier. Now, then what will happen to the design of the fixed pier and foundation? Easy, difficult, light, heavy, economical, uneconomical. You can use all these adjectives and describe uneconomical. So in the case of high seismic zone, if you want all the piers to share the longitudinal inertial effects, then what do you want? The force to be engaged, all of them. But on the other hand, if you made every pier fixed, then what will you do? Then what is the consequence of that? Recall?
It will restrict thermal expansion.
Exactly. You will restrict what? You will remove the breathability of the structure. You understand what breathability I mean? I mean the ability of the structure to expand and contract with minimal internal stresses. That you will remove by making every pier fixed. Then what will happen on daily basis or a seasonal basis? You'll have very large forces. Whereas earthquake is a once in a lifetime, maybe 10 times in a lifetime event, at which time they can all be tested together. Whereas under normal day-to-day operation, you don't want such large forces. So you generally tend to have in long continuous structure one fixed pier, but in a same structure, if it is recreated in a high seismic zone, then what happens is your problem with designing for the longitudinal seismic forces. So in which case you end up installing these shock transmission units. Now, what kind of device is a shock transmission unit? It is a mechanical device. And what is the problem with all mechanical device?
Maintenance.
Absolutely correct. All of you have got it right. So that means this is a maintenance heavy equipment. Now the question is, if you don't do the maintenance, then what happens? At the right moment, it just might fail to perform. Correct? And can you predict when an earthquake will come? Can you?
No.
So therefore, it becomes a maintenance issue if you use this shock transmission unit. So in India, the usage of this shock transmission unit is rare. I'm not saying it is totally abandoned, but it is rare. But let's assure maybe it has been the case in my lifetime that we rarely use it. But you all have a very long career ahead of you. Very, very long career ahead. I'm very sure as a part of the optimization exercise, as you will learn, as you become more and more experienced engineer, you will find the usage of these shock transmission units going up, because as a country, we'll also mature into a more maintenance including country. Okay. I'm sorry, I'm interrupted once more. Please excuse me. Let me take this one phone call. Next time I'll make sure that these phone calls are blocked. Sorry about that. Just give me another. So the shock transmission unit works on the velocity of the movement of this piston. So slow acting, fast acting. So between the, and you have a whole spectrum in between them. So that's how it works. And when you look at the concept, as you can see, this is a conceptual drawing about a continuous bridge deck. Oh, sorry. I didn't share. Share. Okay. Can you see the screen? Okay. Conceptually, you have a bridge. In this case, you have a concept of a three-span continuous structure in which from the inscription, this is the place where the relative displacement between the pier and the substructure is 0. And here you have got a roller bearing, which means what? When the superstructure moves, the relative displacement between the substructure and the superstructure will take place. Okay. So, and the reason why this is done like that, in almost all the bridges in the transverse direction, you always have a one hinge in a pair of bearing. You know, every bridge deck will have at least 2 bearings. Generally, there are certain situations where you may have 1 bearing, but at least 2 bearings in the transverse direction. So one of them is locking and the other one is rolling in the perpendicular direction. So therefore, you don't end up providing the shock transmission. So conceptually, shock transmission units, once they are fixed between all of them, you can see that from a behavior in which only this pier deforms relative to the ground, you will find all the piers will deform relative to the ground with the dotted line if the shock transmission units engage in a seismic stimulation, which is essentially a very fast acting displacement. When a fast acting displacement takes place, then the inertia first it will engage this, but when this start moving fast, there'll be a relative movement at a fast speed happening here. Then this will lock, this will lock, this will lock, and once this locks, then the movement of the superstructure will be also restrained by all the 3 piers. Then the whole system will rock together. That is the concept in which wherein the longitudinal forces due to earthquake will be acting on all the piers instead of only 1 pier if you have the shock transmission unit installed. Okay, so therefore, in terms of the components which transmit force between superstructure and substructure, so we started off in the component. We started off with the superstructure, then we went to the bearing, then we have shock transmission. We are only understanding the broad concept of all this. We look at them in little more detail at a later stage. Right. So next we are going below next level of the components of the bridge system, which is the substructure. In the substructure, we tend to have, typically 3 types of substructure. So we have a wall type pier, or we may have a frame or trestle type of pier. Basically, it means there are multiple columns with a common pier cap, or you have a single column pier. So these are the typically 3 types of substructures which you will notice in all the bridges, right? So to see an example of a wall type bridge, this is a very classical bridge with a wall type pier, and you have a wide wall type. Essentially means it in transverse direction it is very wide, and in the longitudinal direction it is small, and you have a wall type pier all account for this very long span steel bridge. Okay, then you have in a way, this is also looks like a wall type pier only because the width of the substructure is similar to the soffit width of the deck. So this is also in transfer, but this is in concrete, and that one was in masonry. Okay. Another example of a wall type pier wherein you have multiple girders sitting on it on one side. You can see the steel truss on the other side. Again, you can understand by looking at all these pictures, you'll get a clear idea as to what exactly we mean by a wall type pier. Wall type pier is much wider in the transverse direction and much narrower in the direction of the traffic. Then we come to frame type pier. So this is an example of a frame type pier. You can see multiple different types of frame type of pier. You can see one frame type of pier wherein the superstructure is monolithic with a cross diaphragm and it is supported on this. Why do we need it? Because obviously traffic from this side on this road is going along this. So you can't put a pier at this location. And at the same time, you possibly didn't want to do a very long span. So you ended up having one frame type pier. You have another frame type pier going on the backside there. But on the other hand, you have in between a single what is called as a cantilever pier also at this location. So it's a frame pier, cantilever pier, frame pier, cantilever pier. So you have multiple mixtures possible depending upon the local site condition. And at the background, you can see another multiple trestle type, column type pier for the bridge going there. Okay, so this is how a frame type pier or a trestle type pier looks like. So you have other examples of trestle type. These are mimicking cantilever, but in order to reduce the volume of concrete, they have used a concept of a pair of a braced cantilever piers with a small bracing as intermediate height and the pier cap, and therefore this is also essentially a framed pier. Behavior might be slightly different than the wall type pier and the traditional frame type pier. Then another example, an older example of a frame type pier, you have multiple columns, you have a common bed block, and on top of it, you have the superstructure resting or integral with it. So moving on to from the substructure, we have another end substructure, which is we call as abutment. This is generally where the what do you call it? The bridge ends, and this is where the embankment starts. And we have a retention. We generally have an abutment wall, and we have a concept of a wing wall, and you have parapet, deck, and the pier cap. So now the question comes: the wing wall. The wing wall have got two possibilities: the straight one and the bent one. Straight one essentially means something that turns 90 degrees and goes along the alignment, and the bent one is something that goes either totally perpendicular to alignment or a partly perpendicular, as shown in this sketch. An example of a straight abutment is this, where you can see that the abutment wall is there and the return is completely along the alignment. So this is the main abutment wall, and that would be the wing wall. Now, you can have this abutment sometimes in skew and sometimes in perpendicular, as you have seen in the previous example. Okay, so we will move on from this. Is an introduction to the substructure. We will then move to the next part of it, which will be essentially the foundations. So sorry. I have to. Screen is visible?
Yes, sir.
Yeah, okay. So far we have covered superstructure, bearing articulations, substructure, including the abutment. Now we will move on to the foundation, which is the next part of it. So in foundation, what are the types that we generally tend to have? We have something called the individual footings. We have something called the combined footing. When do we use one or the other? When do we use individual footings and when do we use combined footing? My question to you in that case is, in that case, why do you have columns so near? Why cannot you have one column there? So the question is it dependent upon the spacing of the column or something else?
Sir, if the bearing capacity of the soil is low and each footing size is very big, so the footings may overlap. In that case, we can use one footing.
In that, if the soil is low, we use individual footing or use combined footing?
Combined, sir. The
exactly. So therefore, the choice between the individual footing and combined footing is dependent upon the bearing capacity of the soil. If the soil is strong enough and your footing dimensions are manageable reasonably, then you go for isolated footing. And if the soil is medium strength or low strength, then you may end up having, as Shivjit mentioned, you end up having foundation size so big that they start overlapping and you end up using the combined footing, right? Then you have sometimes you also have footings which have got anchors, especially if you end up having tensions in them. So the bridge width with the helical piles, and then you have, after the footings, you end up having piled footing. Have you ever seen this example of a piled footing? Piled footing, not pile foundation. We'll come to pile foundations later. Piled footing. Huh? So where are you likely to see the pile footing? Where are you likely to see the pile?
Where soil bearing capacity is very low and we have to rest it till the rock level. We take pile or to.
It is not a pile foundation. Please understand the difference between a pile foundation. I'm not talking about pile foundation. I said piled footing. So where would you use it? Think about it. It's, as I said, it's only a common sense issue. None of them is very deep technical thing. See, the point is, when you want to do, when do you do footing? What type of foundation is called a footing? In terms of depth?
Shallow.
It's a shallow foundation. So suppose you are in a situation where you are not in a position to do deep foundation. And at the same time, your strata at which you want to put up the foot, you have to do shallow foundation, but the strata in which you have to do shallow foundation is not sufficiently strong, but maybe a little depth below, maybe 5-6 meters below that, you have a reasonably strong strata. If you have that, then what you do is, then you do these kind of piled footing. What do you do? Then you do small RCC piles, which you drive them until the stronger strata, and then create a mat on top of this piles, and then use that mat as the footing for it and do the load transfer. Okay, so we are not doing a deep foundation, but we are doing what is called as a shallow foundation with piles. Okay, so after this, you really end up having a deep foundation. With first of the deep foundation, which you can see is a pile type of foundation, which you would have seen a number of examples if you have started working on any real bridge project. Here, essentially, the idea is you don't have a reasonably strong strata at shallow or medium depth. So you have to take the load transfer mechanism right down to that strata which is strong enough and which is very deep. Once it is so deep, then the first of the option is what is called as a pile foundation. And pile foundation, you have variety of them. You have driven piles, you have board cast in situ piles, and then you have got precast driven piles. So in that sense, you have again, most of them differ in the construction and installation procedures, but nevertheless, they are all deep foundations. But they also have restriction because of their very nature of their construction at what depth they can do. So one of the deepest foundations that have been, most of the very deep foundations have been pile foundation. I don't know if you have been following. There is a bridge being constructed in Maldives by an Indian company called Afcons. They have installed a pile which is around 230 meters long in about 130 meters of water, standing water near in the sea. So board cast in situ foundations can be done to very large depths, right? So in the pile foundations, you have again many choices. You have what is called as a driven piles. Then you have a drilled pile. Drilled pile is you make a bore, install a pile, then they grout it. Then you have you forget about pile footing. We discussed it earlier, but you have inclined piles or the raker piles. They have basically an inclination which you can see as an example here. Now, all of them are used under different driven pile. When you notice it, have you ever seen a driven pile being done? Have you ever seen?
Yes.
How do they do it?
So there is a mechanical device which like impacts with a load on top of it, and
but more important thing is the driven pile is first precast.
Yes.
It has a precast, it has a shoe, and then from the shoe you connect it to a piling rig and then you hammer it down. All right. So when you hammer it down, depending upon your strength requirement and the size of the pile, you choose the hammer, you choose the drop, and with that you know how much energy you are transmitting, and therefore at the end of the driving cycle you are able to estimate the vertical load carrying capacity of the piles. Do you have any idea what approach they use for estimating the pile capacity of a driven pile? How much of your geotechnical engineering do you remember? How much? Little bit, something, a lot of it, none of it. Which option? Yeah. Silence is no good.
So one is like friction that is there with the soil.
Obviously, friction is there. Okay, but I said there's a mechanism by which you can estimate the pile capacity of a driven pile. So, do you recall how it is done? You've heard of the High-Lease method? Energy transfer, number of blows, penetration rate. I want you to do a little bit of reading on that part of the pile foundation to refresh what you may have missed. Okay, so that's a mechanism to do it for driven. Whereas when it comes to drilled piles, it's basically after you do the grouting, you're depending upon your conventional friction and end bearing pile. Where do you use raker piles? That's the next question. Where do you use the raker piles?
Offshore structures.
That is it. Okay, that is I'm now talking in terms of bridges. Where do you use the raker piles? Or even in the offshore, the principle is the same in offshore structure. I didn't mean in that sense where. Okay, why do you use raker piles? If you want to understand that question in that sense. Or when do you use the raker pile? That may be better choice. of question?
To resist more horizontal forces.
So when you have a larger lateral loads, you tend to use Raker piles. What is the consequence of using Raker piles? Yes. The consequence of using a Raker pile. What does it do to the foundation? As structural engineers, you should learn to think in terms of force, displacement, flexibility, stiffness, and things like that. So I've already given you the hint in all that words that I've used. So what does a Raker pile do to the foundation? Stability? Are you telling you can design any foundation which is unstable? So Kalyan, our words should have a precise meaning. Why do you use the word? Why are you comfortable with the word stability? Why do I think that the stability is an incorrect word? Provision of Raker pile in no way improves the stability, but it does something else. What does it do to the foundation? All of them have got a lateral strength. Do you think any foundation has got lacks in lateral strength will stand? No. So what does Raker pile do? I'm reminded of the fact. I shouldn't say I'm reminded of the. It confirms to me that our education system somewhere has
lateral load displacement. It will control lateral load displacement.
And therefore, you're in the right direction, but I want the right word. I'll ask a question. Do you think any foundation that you design lacks the necessary capacity? Apart from providing capacity, it does something else. Nayana was in the right direction, but then she became hesitant. She was afraid to take the next step. Under the action of the lateral load, what happens to the displacement if the piles are vertical and if the piles are raked? This is like me giving the answer.
It will take more lateral load but less vertical loads.
Huh?
When compared to vertical.
Now I didn't even ask that question. I said, what happens to the displacement under the action of a lateral load if the piles were only vertical and if the piles were raked? That was the question I asked.
So for vertical piles, bending moment will be induced in the piles more, and for Raker piles, it will be axial forces.
I asked about displacement. You've gone towards the force. This reinforces my idea that Newton's law and the introduction of Hooke's law for us in the 8th standard is something that prevents, that actually twists, or I should say, doesn't word twist is not the word. It curtails our thinking capacity as we go to higher and higher classes. I talked about this. So, and therefore, what does it mean if the displacement is less? At last. So therefore, what does the Raker piles do? They increase the horizontal stiffness. Now I'll ask you one question. Under what circumstances are the horizontal force likely to be highest? Under what condition?
Seismic conditions.
Huh? What did he say? I didn't hear it.
Seismic conditions.
Seismic condition. But in the seismic condition, is a very steep foundation good for you? So now what do? Lateral Raker piles are very good for taking large lateral forces, but in seismic conditions, I don't want very large stiffness. Our engineer's life is very miserable, right? The solution that is most suited for large forces is very bad for earthquake condition, which produces the largest horizontal forces. Correct? So my question to you is, when should you use the Raker piles? So where should you use Raker piles comfortably? Huh?
So we use it in offshore structures where tidal loads are.
Yeah. Okay. So there basically, otherwise your foundations are so flexible that your earthquake is not important. I also extracted the answer from my mouth itself. You use Raker piles when earthquake is not the largest lateral load causing effect. In your normal bridges, which element sees the maximum lateral force in a non-seismic situation? In a non-seismic situation, which component of your bridge system sees the maximum lateral load? We just went through it about 20 minutes back.
Wind forces.
Not necessary.
Braking force.
No, there is one component which always sees. I just said 10 minutes back we discussed this, maybe 15 minutes back. No.
Bearings.
No. All bearings will. No. One by one, all guesses are coming except the right one.
Supports.
Who was that? Me, Sukalyan. Abutment is the one which has permanently a large lateral force due to what?
Soil.
Earth pressure.
Earth pressure.
Correct? So that is where you can ideally use a Raker pile. Think simple, huh? Don't think very complicated. I think we'll take through the simple, we'll go to the complicated by the time we are about 5 months down the line. We will discuss really complicated stuff at that time. Okay. So Raker piles are a blessing and a curse. Blessing for permanent lateral loads and a curse for inertial based lateral loads. Right. Then we go to the next large type of deep foundation, which we call as a well foundation or a caisson foundation. Have any one of you seen a well foundation? Possibly not. Most of you have been working for what? 2 to 5 years? Have you been to the site? No, I shouldn't ask that. I think most of you don't like going to site. Yeah? Have any one of you visited site and seen Quezon Foundation anywhere?
The second Hooghly Bridge.
Yes, second Hooghly Bridge is a Quezon Foundation, no doubt about it. But I haven't seen it because it was finished before I started my career.
Some rehabilitation work is going on, so
yeah, but are they doing it for the foundation or they are doing it for the deck and these pylons and things like that?
Mainly for bearings, and
expansion joints.
Yeah.
But I'm asking, have any one of you seen a well foundation, a Quezon Foundation anywhere? If I were to think about it in which one of our current projects they are doing. Okay, something it's a legacy project. I think most of the well foundations are over, but if anybody is from Bihar, if you can go and make a visit to Kachi Dargah, they might be doing a few well foundations still. You have to ask Shastri for it. Arrange to go there and see if they are doing it. Okay, so not too many projects which they do well foundation because it's a very slow process. So it's not preferred nowadays. Most of them try to find a pile substitution for that. Now, in well foundation, you have, as you can see, the parameters L by B. Okay. I'm sorry, I need to take one more break. I'm very, today is not a good day. Need too many breaks. Moving on to the well foundation. I would like you to tell me what kind of relationship should a well have with regards to L and B, where L is the depth and B is, say, the diameter. What kind of relationship should they have?
Inverse relation.
Inverse relation means?
If length is more, the dia is.
That is okay. That is relativity. I'm telling, and in an absolute sense. Can I have L equal to B? Huh? Why? Why 2B? Okay, so what you mean to say is, suppose I have a, remember well foundation is a deep foundation. So let us say we have a 30-meter deep well to do. So that means the diameter should be 2/3 of about 20-meter diameter. Or 15-meter diameter. If it is 2, if it is 1.5, it will be 20-meter diameter. The depth diameter should be more, should be very large. That is how it will be the criteria. You cannot have 1:1.5, 1:2, or 1:1. It has to be much more than that. So typically you could say that it should be at least, if nothing more, you should have at least 5 or 6 should be the at least. And though for it to be classified as a deep foundation, the ratio could be much higher than 5 or 6 also. Okay, if it becomes very small, it will more or less behave like a shallow foundation. Then it will not be a deep foundation at all. Okay, so in transverse section, sometimes we have to adjacent well next to each other. You have any idea how much separation? Should there be a separation at all, or can it be touching each other? Yeah. How much separation should be there? How much separation should be there?
Minimum 2B.
Minimum 2D is what? When you talk about 2D, then you should talk about minimum separation. What is it? You're talking about
Face to face.
Clear space.
Clear space.
Clear space should be 2D. Okay. I'll give you an exercise. All of you go to whichever code is relevant to it, and can you find out that next class? Next class, find out what should be the minimum clear gap between two Kazon foundation. Okay. I won't tell you what code to refer, what standard. I want you to do your own study and come back and report in the next class. All right. Next question. Can the founding level be different? When you have two foundations close to each other, can the founding levels be different?
It depends on the stiffness of the soil strata.
In what sense does that control the level difference? The question is, they are close to each other. Next class, you will find out for me how close they can be, and if they are that close, can there be level difference in their founding level? And if so, by how much? You will always have, whenever two foundations are next to each other, the question that is always asked during the construction stage is when it's most critical, because you are doing an empty excavation. So at that time, all the kinds of thoughts will come in. What happens when I'm doing an excavation next to an already existing foundation? So in a similar sense, you need to answer yourself and satisfy yourself that you have the right distance and right level difference between them for it to be a safe construction. So you find that out also next month. Okay. Then you have different shapes possible. This is what is a pure circular. And this is what is a oblong one, sometimes called double D because there is a D here and a D here. Sometimes they have 3 chambers. Sometimes they have only 2 chambers, 2 Ds together. Now there is something that I want you to answer from common sense only. Which of them do you think will be easier to install? Circular one will be easier. The other one is not easy to install. Why? Internal walls. Now this is where, now that means the question is the construction of this is not understood. This is never, it is done in bit, always all the extension of the well is sunk piecewise. They cast 1.5 meters, they sink it. Then the original top, which was 1.5 meters above ground, will come to the ground level. They extend the shuttering and the cost, everything, all the casting of the wells, walls and steening, which is called a steening, is done at the ground level. So that is not a problem at all. That is not the reason why installation is difficult. How do you think they extract the muck from inside the well? Okay, let me go back to maybe this is a good example. The way this is built is, I think all of you should know a little bit of construction of how this well foundation is constructed. The bottommost portion first is cast at the ground level. Is cast at the ground level, and this bottommost portion is called the curb. And at the sharp corner, you have something called the cutting edge that it helps in what they call it sinking of the well. The process of putting this one, which is cast at this level up to this, is called sinking. Have you ever seen a well sinking done? Any kind of well sinking?
Videos only, sir. Actually, not videos I seen.
Only you have seen. Okay. So basically, what they do is they cast about 1.5 to 2 meters of this bottom portion at the ground level. Then with a grab, you know what a grab is? A crane in which there is a cloth fixed with which you fix and remove the soil. So you remove this soil. When you remove the soil underneath this, under the weight of this, the well starts to sink because there is no resistance in the inside portion of the well. So the grabbing operation removes the soil from inside, enabling the cutting edge to cut through the soil and sink. And then when this 2.5 meters, that which was at this level, it sinks down and comes to this. Then they add another 2 meters of shuttering, cast that portion of the well steening, then grab further. The moment you grab further, the internal resistance of the soil is destroyed. So what happens is, under the weight of the steening, it sinks further. That way, progressively, you keep on casting and extending it. So construction of the steening is not a problem. But in this process I have described to you, introduces a certain complication in sinking. Can you guess what that complication would be?
It might not sink vertically.
Exactly. Why not? Correct. But normally in a space like this, you cannot have two cranes sitting and operating. This is not as if this is 50 meter wide. Most of it is about 10 to 12 meter dimension this way, maybe 3-4 meters clear opening like that. So in that case, what happens is these two openings, though in this sketch looks wide, but if there are only two openings, they're very close to each other. So you cannot operate cranes so closely. So you end up using one crane. One crane means it will grab in this and then it will grab in that. So with that, what happens is when you grab first, say, let us say you grab on the left hand side first. So soil resistance at the bottom is gone in this chamber. So this tends to sink. Then by the time you come to this, this is already tilted a little bit. And then when you grab it, it may or may not correct itself fully. So you are now depending upon providence to give you a correct well. That is why it is not preferred to do a non-circular section. Not preferred. But if unavoidable, it is done. Okay. So if you take a look at it, in all the foundations, you have shallow foundation, you have a piled shaft, which is called as a single pile solution. It is being adopted in some of the foundations of high-speed rail. You have a well foundation, you have rake piles, you have vertical piles, and you have a piled footing. These are all visually to tell you in one all the ways in which the foundations can be conceptualized. Right now, if you want to look at the what do you call it, choice of foundation, how do you choose which kind of a thing you do? So you primarily look at the strength to strain ratio. So initially all of them very stiff, and after some time, for the additional load, because soil is definitely not a linear behaving material, it will tend to lose its stiffness very quickly, and after some time it lose so much that you will have what is called a large displacement failure. Okay, so when you have this kind of a behavior between soil and any foundation. We don't talk in terms of strength of soil. We talk in terms of, okay, you can look at its strength and flexibility, but the two important parameters is soil is strength and the flexibility. So if the soil can have a high strength and low flexibility, soil can have a medium strength and medium flexibility, and it can have a high flexibility and low strength. Okay, in all these combinations, when you have, especially when you see the what do you call it, and then the question, the depth of the foundation, also small, medium, and large. So in that you end up with a matrix. So where do we avoid foundations altogether? We avoid foundation in low strength of soil with very high flexibility. We try to avoid putting any foundation in that. So this is the one which is to be avoided. When you have medium strength of soil and have medium flexibility, we tend to choose, and for a large depth, we tend to choose well foundation. And if the depth is medium, we tend to use pile, and if it is depth of foundation is small, we tend to use combined footing. And why we go for combined footing? Because the soil strength is medium. But if the soil strength is high, even if the flexibility is low, that means a very stiff soil or rigid soil. In that case, we end up using individual footing. And if the stiffness is medium stiffness, then we use combined footing. And if we have a large depth of foundation in the same kind of a strata with high strength and low flexibility, we end up using piles. Okay, so obviously for all this, the capacity will also vary. So this is a nutshell of matrix in which you will end up seeing the utilization. Of course, there are always some outliers in which you end up choosing different set of arrangement which are also incorporated in certain foundations. Okay, let me see. Next is the load path concept. I'm wondering whether I should start that now. We are at 5:30. So I will commence with we will have a round of question and answers from now until 6 o'clock on what we have seen in the last two classes and what we have seen today in terms of the soil, foundation, articulation, substructure, and superstructure. The floor is yours. Yes, please. Anything in your mind as a question over the last 2 days? Yeah, go ahead. Okay. See, there are two aspects to the word impact. Okay. One impact is actually due to the roughness of the road surface. That causes one impact, and the other one is not actually an impact. It is what is called as due to the dynamic nature or dynamic action of the moving load on a bridge structure. So if imagine that it doesn't normally happen on a bridge deck, but imagine that you have a pothole on a bridge deck, or if your bearing course has been partially damaged, then what happens is when the moving load goes, it suddenly comes with an impact on the bridge. So this effect, along with the dynamic, is felt more in smaller spans. But as the span becomes larger and larger and becomes flexible by itself, then you will find that this so-called dynamic effect is much less. Therefore, you will have a graph. You will see for short spans, you have a very high impact factor, and for a longer spans, you have a lower impact factor. But this problem for road bridges is less if any of you get a chance in your later life in your career to work on railway bridges, and particularly medium speed and high speed. There are a lot of dynamic analysis to be done to assess the what is called as a dynamic amplification factor. What is an amplification factor? This is different from impact factor. Remember that on road bridges, we neglect the dynamic amplification. The dynamic amplification in road bridges is only considered for wind effect in very long span with very flexible deck. Only then we look at the dynamic amplification. But as far as the live load amplification for road bridges is not considered so significant because of the randomness with which the road load actually plies on the bridge deck. But if on the other hand, if we had a railway bridge, whether it's a medium speed or high speed, then what happens is there's a particular periodicity of the axle load. And depending upon the speed at which the train is moving, the flexibility of the span and the dynamic characteristic and natural period of the bridge deck, then there could be a situation wherein you could have what is called as a resonance between the arrival of the load and the natural oscillation of the bridge deck. When this coincides, there is a certain amplification to the gravity effect. That is called the dynamic amplification. You will see a term which is called CDA, coefficient of dynamic amplification. You don't, in that case, they do not use the word impact factor, but sometimes there's a confusion whether the impact factor of the bridge is the same as the dynamic amplification of the railway bridge. They are not exactly the same. But sometimes you might see the formulation are very similar, and that is what actually confuses many people. The dynamic amplification depends upon the natural frequency of the deck and the periodicity of the live load. And the periodicity of live load is not ensured or not at all guaranteed in a road bridge. And therefore, we do not look at the dynamic amplification for road bridges as much as we look at it for the railway bridges. So your question about the impact factor in road is primarily dependent upon the surface roughness, primarily dependent upon surface roughness, magnified by the flexibility of the deck, magnified or reduced by the flexibility of the deck. The more flexible the deck, less is the impact factor. I forgot last time I wanted to ask you how much of your extra reading is going on beyond this Friday, 2 hours. Silence means something. None of you have gone close to any of the reading materials. Okay, so in that case, what we will do is we will, if there are no further questions, I would like to call it for the day. The next section is the load paths and the load transfer mechanism. It's a little more intense. I don't want to have a break in between. I will start that afresh in the next. By the way, is next Friday a working day? It's a holiday, right? So when do we do a compensation? That depends upon when I am able to come to the office. Can I let you know sometime in the early part of next week when we will have the compensatory class for the next Friday? Okay, so you must have that. Huh? Okay, my program for the next week is not firm yet. I will check on that within today, later in the day and tomorrow. And by Monday, I will let you know when that class is to be, because I don't want to miss any week. So if it's holiday, we will choose another day. I will talk to HR and also tell them to be a little more flexible in allowing that 2 hours. Okay. All right then. If you have no further questions, we will meet next class. I thought it was next Friday, but it struck me that it is holiday. So I'll let you know about that. All right.
Okay, sir.
Sir,
Okay. Yes.
sir.
सर वो जो
Yes.
एक क्वेश्चन था जिसमें हम आप पूछे थे कि इंटरमीडिएट स्टीफनर यूज होगा, सॉरी डायफ्राम यूज होगा या नहीं होगा बॉक्स गटर पे, तो सर उसका आंसर फाइनल सर डिस्कस हुआ नहीं है सर?
उसका आंसर we will discuss it when we come to discuss the see, we have now got I put this question to you so that when we are discussing that in detail, you'll get. Meanwhile, I still would like you to search for it, because we'll come to that, because as we progress, we have now started just introducing the component. Then we'll start to load path. Then we look at the behavior. When it comes to behavior, you will get an answer to it, or at least you'll get a hint of an answer to it, because I don't believe in giving the answer. I want you people to discover the answer. The answers you discover will remain longer with you. The answers which I tell you will remain fresh in your memory for a short while, and then it will be forgotten. So meanwhile, I leave that to you. You can find out for yourself whether it is required, not required, when it's required. But nevertheless, when I come to the section where we are talking about box girder behavior, at that time you will get to know about it. Definitely, I guarantee it. But meanwhile, that's it. That's coming sometime, because I have structured this program in such a way that we progress slowly, so that I raise questions in your mind. You should also have questions in your mind. Some questions I would like to answer at that time. Some questions I will park it for another day. Okay. Right then. All right then. See you in the next class.
Also no problem. In 5A also, if you see.
Excuse me? I didn't hear what was said. All right. We'll meet next class. I'll let you know about the timing, because next Friday is a holiday, if I'm not mistaken. That's according to what I have seen in the calendar. Or is it a... Oh, call dropped. No. Are you able to hear me?
Yes, sir.
Yes, sir.
Okay. I have seen that as a holiday in the calendar that I can see in Chennai. Is it a holiday throughout all our offices?
No, sir.
Okay, fine. Right. So I will let you know when that can be a compensation for that, which day, and I will discuss with the HR and get it cleared with them beforehand. All right.
Yes, sir.
Okay, sir.
Okay then. Right. Good night.
Thank you, sir.
Thank you, sir.
Thank you.